And here are some electronegativity values, and you can see that hydrogen and carbon, here's our scale here, have roughly the same. Carbon has a slightly higher electronegativity value, but they're roughly equivalent, whereas oxygen up here has a much higher electronegativity value and therefore grabs the electrons much more tightly. Note that nitrogen is very similar to oxygen, and therefore if you were to look at nitrogen bonded to hydrogen, you would find that nitrogen acquires a partial negative charge and hydrogen acquires a partial positive charge in that case as well. So if we were to look at NH here, another H, NH2 here, or NH3, let's say, the nitrogen here will acquire a partial negative charge to it, and the hydrogens will acquire partial positive charges. And this has consequences for how nitrogen bonded to hydrogen can participate in what we'll call hydrogen bonding. So now we're going to move on to hydrogen bonding, and we're going to use water as our example for hydrogen bonding, because the hydrogen bonding of water has very important consequences for life. So let's look at that right now. Life is inextricably tied to water. The key feature of water, the most outstanding chemical property of water, although there are others that are important for life, is its ability to form hydrogen bonds, and that has many consequences for the way water behaves. So we've talked about how partially negative oxygen atoms and partially positive hydrogen atoms of water molecules come to be, and then we can look at how those will form bonds with each other, how molecules of water will form bonds with each other. But before we do that, I thought I'd share with you one of my favorite quotes about water. It's not from science, it's from the literature, and it's from Even Cowgirls Get the Blues by Tom Robbins. So I'll give you a minute to read this over. It's rather amusing, and it's on the opening page of Even Cowgirls Get the Blues, and it has some basis in science. So it's an amusing quote, and I'll just leave that with you now for a minute. So if you need more time to enjoy that quote, you could just pause the video there. So we've already talked about the polarity of water. We've talked about the polar nature of the water molecule due to the greater electronegativity of oxygen over hydrogen. And we've talked about the partial charges that develop. And so if we look at water in three different ways, here is the Bohr model. Looking at the shared electrons here between hydrogen and oxygen, showing the partial positive charges on the hydrogens and partial negative charges on the oxygen. And then here's a ball and stick model where the atoms are represented as balls, roughly to scale with their diameters. Oxygen has a larger diameter than hydrogen does. And when we draw these molecules, the bars between the balls represent the shared electron pairs. Those represent the covalent bonds. And water has what we would call tetrahedral symmetry. If we look at the charge distribution, we would find the partial negative charges on oxygen distributed as follows, and the partial positive charges on the hydrogens as follows. So there's really a tetrahedral arrangement of the water molecule when you look at the charge distribution. And then if we look at a space-filling model, here when we draw space-filling models of molecules, and we'll be viewing a lot of these as the course goes along, the radii are meant to represent the radii of these spheres in a space-filling model are meant to represent the diameter of the electron cloud surrounding a given atom. So oxygen has is a much larger atom, and therefore it has a much larger electron cloud than either hydrogen. Again, showing the partial positive charges. Now, the polar covalent bond nature of the water molecule produces the phenomenon called hydrogen bonding. And so this is the third type of chemical bonding that we're going to be talking about. We've done covalent, we've done ionic bonding, and now let's look at hydrogen bonding. And so let's look at this with water for a second. Given that every water molecule has partially positively charged hydrogens on them and partially negatively charged oxygens on them, this means there will be an electrostatic attraction between the hydrogens of one water molecule and the oxygens of another water molecule. And that electrostatic attraction draws the water molecules together in what we term a hydrogen bond. Now, a hydrogen bond is like an ionic bond in that it's based on electrostatic attraction, but because these are partial charges and not full charges, as is the case with ionic bonds, the hydrogen bond is much weaker than an ionic bond under normal circumstances. So another way of looking at this hydrogen bond is that in the example shown here, this water molecule, this oxygen in a way, is donating its hydrogen to this oxygen. And we could call this oxygen then the hydrogen bond donor, and this oxygen the hydrogen bond acceptor. And in a way, another way to think about it is that these oxygens, these two oxygens on these two different water molecules, are kind of sharing this hydrogen due to that electrostatic attraction. And that is not just restricted to water hydrogen bonding between water molecules, but you can also have hydrogen bonds between, let's say, water and a partially charged hydrogen in some organic molecule. Now, this will become very, very important when we talk about protein structure. And we'll be visiting this again and again. Hydrogen bonds will be very important. And when we visit DNA structure as well, hydrogen bonding will be extremely important. But returning now again to water, the hydrogen bonding of water has some very important consequences. One is that water exhibits cohesion, in that the water molecules that are attracted to each other provide for cohesion of even liquid water. And although each individual hydrogen bond is weak, as we've pointed out, and transitory in that it can be broken. The water molecules are moving around and hydrogen bonds are forming and breaking, and there's a non-static situation there. The cumulative effects of all these hydrogen bonds are very enormous. And that hydrogen bonding is responsible for many of water's physical properties that are very important for life. So here's an example of water cohesion. Cohesion provides for surface tension, and here's a little water strider walking on water, utilizing the surface tension present on water due to the hydrogen bonding that's going on in liquid water. Also, because water molecules stick to other polar molecules, not just water, there is the phenomenon of capillary action, where water will rise up a tube because the water molecules cohere to charged surfaces like the glass surface. And that capillary action is very important, for example, in the transport of water in plants. So another property that hydrogen bonding of water yields is that water has a very high specific heat. You need to put a lot of energy into water. You need to apply energy to water in order to change the temperature very much, because you've got to break hydrogen bonds in order to increase the kinetic energy of the molecules in solution. So you need a lot of energy to change the temperature of water. And as you probably know, large bodies of water can buffer temperatures on terrestrial habitats that are near them. So oceans, for example, make it they create a milder temperature on adjacent land masses than would otherwise be true because of the large body of water having a high specific heat. So that buffered that temperature, the climate is buffered by water because energy has to be put into water in order to change its temperature. Water has a high heat of vaporization because of that, the attraction of one water molecule to another. And therefore, when water evaporates from a surface, that causes cooling of that surface. And lots of animals use evaporative cooling, and plants for that matter, use evaporative cooling as a way to regulate temperature. Now, another feature of water and hydrogen bonding of water is that ice, that is solid water, when you cool water it forms ice, as you know, that is actually less dense than liquid water because of the hydrogen bonding lattices that form when ice crystals form. And the one important consequence of that is that bodies of water freeze from the top down because ice floats on water. If that weren't the case, most of the major bodies of water on Earth would be ice, except for a very thin layer of liquid water that would thaw out during warm seasons. And life would be vastly different on Earth if that were the case. So that is important also. Now, given that you understand the molecular properties of water, it's interesting to consider the dynamics of water freezing, liquid water freezing into ice, or alternatively, crystalline ice melting into liquid water. And we'll give you two links to some interesting movies that show those molecular dynamics. Now let's consider some other properties of water. Because of its polar nature, water bearing partial positive and negative charges, water is an excellent solvent. So for example, salt, as you know, table salt dissolves very easily in water because the positively charged sodium ions and the negatively charged chloride ions in a salt crystal, in table salt crystal, can be solvated by the negatively charged oxygens surrounding positively charged sodium ions and the partially positively charged hydrogens on water molecules solvating the negatively charged chloride ions. So water is an excellent solvent for polar substances like salt crystals. So in the last part of this lecture, we'll talk about some additional features of water and finish by talking about the nature of chemical reactions.